Oh, well, we can wait 1 second. What do I do with the Monday 11? I can erase. Okay, so recall yesterday we had said that an algebraic stack is a special kind, is a generalization of a scheme which can be viewed as a functor or a pseudo functor from scheme up to groupoids, and in particular the complex valued points are a groupoid, or the geometric points are a groupoid. So when you have a moduli problem, when the automorphism group of different points are different, you usually have a stack in front of you, and if you ignore it, you do it at your peril. And I also explained that there is a special kind of stack which is easy to describe. So the extra assumption, so which kind of algebraic stacks are allowed, algebraic stacks means that this is a pseudo-functor associated to an internal groupoid in the category of scheme, and schemes are to you. And this is something very long to write down. All you have to remember is that these morphisms have to be étale for a Deligne-Mumford stack and smooth for an Artin stack. And more generally, if I have an Artin stack such that each automorphism group of each geometric point is étale, then it actually is a Deligne-Mumford stack. So this, as I said, defining this internal groupoid is long. So the special case is of groupoid is a group action. And if we fix over a base scheme, or in fact you could even fix a base algebraic stack, doesn't matter, then you take a G X scheme. Let me start with a base scheme. X is scheme and G is a group scheme. And then you define the quotient stack by giving explicitly the groupoid as follows, by defining X mod G computed on a scheme S is the set of the objects are diagrams where P over S is a principal G bundle and P2X, sorry, GX on X, and P2X is G equivariant. And then I have to tell you what are the morphisms, and the morphisms are isomorphisms of G bundles such that the morphisms to X commute. Notice that this is really to X, also to S of G bundles over S. Sorry. So these are the objects, these are the morphisms, and how the pullback happens is kind of clear. So today we go back to our original problem, namely to give a geometric counterpart to the derived category. So in particular, what I'm interested in, remember that if X is a scheme with enough locally frees, then every object in the derived category from -1 to 0 cox can be written this means can be written means is isomorphic in the derived category too as E minus 1 to E0 with E0 locally free and E minus 1 coherent. And the special example of this we were interested in was if we have a morphism which has a global factorization, then we can consider I mod I squared to the pullback of the relative tangent band. So what we want to do, if we have this, we want to associate to such an object, we can associate a stack, an algebraic stack over X with an A1 action, where A1 action means it's a multiplicative action. So it's a map from, well, if you want, it's like a GM action, but you put A1 instead of GM, and multiplication is defined on A1. So how do I define it? Well, what I can do is I can call E0. I hope the difference in character is clear. This is math-cal and is just straight letters. You have E0 to E1, where EI is spec sim E minus I. Oh yes, and here I had assumed that G was smooth. Oops. We can weaken this assumption, but we don't need to do it here. So this is a homomorphism of abelian groups, abelian group schemes over X. So in particular, it defines an action of E0 on E1 by translation. And so what I can do is I can form that what I do is I construct, and then I think the name something like this, but since this is very long, I will just call it H. Or sometimes when I feel that no confusion is possible, I will write it as E underline. E underline is actually typically this would be a math frac E, but you can choose for readability what is best, because I don't know how much people like math frac, so I can't draw it anyway, so that's why I underline. But you can just keep this one or this one in the notes. It's no difference, just for clarity on the blackboard. So this here is defined to be the quotient stack of E1 mod E0. And this is defined because, after all, E0 over X is a smooth affine scheme. So this is defined because so E0 over X smooth. And smooth. So, and as I told you, now I want to tell you how the A1 action comes to pass. So, of course, A1 acts on E0 and E1. And so I can act on the quotient. So how do I do it? Well, if I have, so how do I say that it acts on E? And the answer is, well, you take an element P over S to E1, where P is a principal, S is an X scheme, and P is a principal, let me call this G, little s, as pullback of E0. Yes. Sorry, this is it's an upper. Sorry.
And also capital E1 or capital E minus 1? Why capital E1?
No. The capital E, I decided to change the indices because I want to separate who are the coherent sheaves, which I regard as sheaves, and who are the bundles or abelian cones that I regard as geometric objects. So let me insist that this is a math cal E, and this is just an E. So I think that is kind of okay so far, but this is definitely an A1. I don't have an A lower one. So this is a principal as pullback of E0 bundle. So this is just another vector bundle. So it means that there is an action fiber-wise of this bundle on P. So how do I, if I take now lambda as action from S to A1, and here, of course, I forgot to say we always work over a field today. And all the schemes until are schemes of finite type over this field. So, given such a morphism, so I want to define how lambda acts here. So this is a section of the group A1. And how does it act? Well, lambda clearly acts on this. So what I do is I multiply. I have my original picture, which is my action here, and I compose it by, here I take multiplication by lambda and the identity. So this is my original action, and this is my new action, lambda of A. So what I've changed, I've kept the same. Of course, it's isomorphic. I mean, it's clear, but it is an action, and what you can check is that you get still you can still get an equivariant map to E1, but because by getting rid of the action on the E1 side. So to get an equivariant map, so then to get an equivariant map to E1, you have to also multiply there. Anyway, so this is very informal. The reason why it's informal is that if you want to go and write down exactly what it means to have, you know, when I say action, we all learned very early in our career what is an action of a group on a set. And then from there we learned what is an action of a Lie group on a manifold and what is an action of a group scheme on a scheme, etc. But here actually there is something I'm not telling you, which is what is an action of a group on a stack. So again here there is missing the notion of group actions on groupoids and therefore on stacks. So again, just like once we had defined the action of a group on a set, the definition of action of a group scheme on a scheme wasn't conceptually difficult. I mean, the actions were the same. We just had to make sure that some maps were morphism of schemes. Here the point is we have gone out of categories. We are inside two categories, so we have to. It's not terribly difficult, but it's something that requires, in the definition, the associativity relation, so the fact that action is an action, becomes a two arrow, and then you get a nice cube or whatever it is, which has to be two commutative. So this is not difficult, it's something simple, but you have to write it down.
So the group action on groupoids is the analog of the A-value points acting on the stack.
Yes. So, and then once you know this, then basically to say the action of a group scheme on a stack means that for every S, you have an action of the group on that S on the groupoid on that S, and that this is all compatible with pullbacks.
That would be the meaning of the group action.
Yes. So the key point is to write this one down, and everything else is just that you do it like when you do the action of a sheaf of groups on a sheaf of sets. It means for every open you have the action, and then you have that it's compatible with all the restrictions. So
A1S is a group scheme over S.
It's not a group scheme. It's a semi-group.
Semi-group. Okay.
It's a semi-group. No. I view it as multiplicative. Actually, this is what you write. But in fact, you could as well. I think you could as well use GM.
It's a GM group scheme extended.
Yes. I think you can as well use GM. The problem is, the reason why I think the best way to say it is that it's a group GM action where the action map extends to A1. The point is, for schemes, this is basically the same, because I typically think of schemes as separated, while Artin stacks are nowhere near separated. So if you want that your GM action stands to a specific A1 action, then you better write it down.
This is not just.
Yeah.
This is GM action acting on that arrow E0 to E1.
Well, it's acting on the stack. So you start, the point is that you have here GM acting, the action is here, and this map is equivariant, and hence it goes down to the quotient, basically. Oh, sorry. And yeah, so on here.
Yeah, because this diagram is an object in mass track E of S, this diagram.
Yes.
E going to E and E going.
So what you get, so what I have done is I found a way to associate to such a morphism an algebraic stack with an A1 action. And the next thing you can check, it is there you can make proposition. And this is actually not difficult to prove, and it doesn't have with this A1 action, it just means understanding how the definition of algebraic stacks works. So assume given a commutative diagram of coherent sheaves on X, with E0 and F0 locally free. Well, then to both E minus 1 E0 and F minus 1 F0, we can associate the corresponding stacks. So the point is then, well, in particular, we get, hence, we also get a commutative diagram of abelian cones and here we have, remember, you just have to reverse all the arrows. It's, if you want.
So there's something on the quotient points is what we have to focus on.
Exactly. And so the lemma, the proposition says one is that the diagram induces an A1 equivariant morphism of algebraic stacks F to E to, let me call this H of phi, because after all that's what it is, and to H of phi is representable. Remember, by definition, this means that when you base change with a scheme, you get a scheme, i.e., when, well, in principle, you get an algebraic space. You base change by a scheme. But in this case, you really get a scheme, not just an algebraic space. So if you want it strongly representable, even only if the H0 here is surjective. And 3, H phi is a closed embedding. So this means that every base change by a scheme is a closed embedding of schemes, even only if H0 phi is surjective and H minus 1 is an isomorphism and H minus 1 phi is surjective. And finally, H phi is an, remember, for algebraic stacks, to say that they are isomorphic, it doesn't mean that for every schemes the two groupoids are strictly isomorphic, but it means just that the morphism of only groupoids is an equivalent. So it's an isomorphism of algebraic stacks, and this means, if you want, it means that whenever you base change by a scheme, you get an isomorphism of schemes, even only if phi is an isomorphism, is a quasi-isomorphism, i.e. induces an isomorphism in the derived category. So let me give a sketch of the proof of this, because this is, I think, a key result, and it's not difficult. So, yes? Oh, thanks. 5, if alpha from E0 So F minus 1 is a homomorphism of coherent sheets hence defining psi 0 homotopic to then alpha induces a two-morphism H of alpha from, and now I have to decide which way round, so let me say that it goes like this, but it might be that it goes the other way around. Anyway, it's an abelian group, so it's and all two morphisms are invertible, so possibly the other way around. Okay, so how do we prove this? So proof. So 1 and 5 are actually analogous to what we have seen for abelian groups yesterday. So we have seen that for abelian groups we got these strict abelian groupoids, and the commutative diagram gave us a map, and the homotopy gave us a two-morphism. And this is completely analogous. So 1 and 5 are kind of same, just if you want, they just use for every S X scheme, you have the section of everything over S, so you have a commutative diagram of abelian groups. And basically this is the only idea, except of course now you have these principal bundles, so you have a little bit more of attention to pay. But you see, for instance, if I have P, where do I want to go? If I have a principal bundle over, which is it, F0, I get a principal bundle over E0 by doing an appropriate fiber product. Or the way I think of it, principal bundles are an element in H1 of the group, and so I get an element in E0, sorry. So if I want to, if I have P to X in F1 to S, where P S goes to X, and S and P is a principal S pullback of F0 bundle. So to such a principal S pullback, since I have a S pullback of F0 to S pullback of E0 is a group homomorphism. So, a group scheme homomorphism over S. Then I can associate to P by doing fiber product. I can associate to P a principal S pullback E0 bundle P twiddle. the way I think of it is that a principal bundle is given by a Čech cocycle, and then I just map each component of the cocycle from this to this. And then, of course, what I get is I had my original P, which goes to F1, which goes to E1. And what you can prove is by definition of P twiddle, and since using that diagram commute, you get that there exists a unique map here, making the diagram commute, so that this is actually induced. And similarly for the two morphism, and I will not write this down. So this is kind of the elementary part. The reason why these two get put together is because these two are global. Oh, and then of course you have to prove that everything is A1 equivariant. And everything is A1 equivariant. So that is the easy part. And now the point is 2, 3, and 4. The point is these have to be proven globally. But 2, 3, and 4 are local statements. Because the property for an algebra, local, for instance, in the Zariski topology. Because the property for a scheme, for an algebraic stack to be a scheme, is certainly locally true in the Zariski topology. And the property of a morphism of schemes to be a closed embedding is local in the Zariski topology, and the property of being an isomorphism is local in the Zariski topology. Which means I can assume that X is affine. And once you are over an affine scheme, then you have enough projectives, or in fact everything. You get all these schemes are free and everything becomes very, very easy. Also, you see, when you try to make a, then everything becomes very, very simple, and you just write it explicitly. In particular, to check this condition 2, the first thing is that if for any base change by a scheme you get a scheme, the first thing you want to do is you want to check on a geometric point, because geometric point is a spec of a field, is a scheme. And what you do is you check that this immediately gives you this. And once you have this, then it's very easy to check. Since you are on an affine scheme, once this is surjective, you can actually assume that these two are the same. And then you are in then basically nothing anymore happens. Once you have proven point 2, and you can assume that E0 and F0 are the same, then everything is local, so you can read it up on this side, and then it's precisely what we had already seen, that the morphism of so this becomes kind of very simple. So this is basically the idea, and I will not say more about this, but what I want to point out is that this is an elementary proposition. It's a good exercise for somebody who has digested a little bit the definition of what is a quotient stack, and who knows principal bundles, of course, and what an action is. So the important thing is, so far this is not complicated, but the important theorem, and here in the proof you actually, so that's why we go here. Actually, let me start with a definition before having a theorem. So definition, let X be a scheme, and abelian cone stack over X is an algebraic stack E over X, which Zariski locally on X has the form H of E dot for as before. Sorry, is an algebraic stack with A1 action, and the locus is isomorph is A1 equivariantly isomorphic to some for some choice of morphism as before. So the idea is to such a simple object we associate a stack with an A1 action, and then we define a global object which has the same properties, still a stack and still has an A1 action, and we require that it locally it has the same form.
It doesn't even come globally from R2.
That is precisely, so that's precisely where you need to go and copy the theorem of the proof of Deligne, and you get a priori it doesn't have to come from a complex, but in fact it does. So theorem, there is an equivalence. And this is in a paper with Kai Behrendt, but honestly I would never have been able not just to prove this theorem but even to write it, because I wouldn't be able by myself at that time to read the paper of Deligne. Still now I find it hard going. I've been anyway, so this theorem says that there is an equivalence of categories. Notice we have categories, not two categories here, from d minus 1, 0, x co for every x scheme. Notice that I'm no longer assuming that there are enough locally frees. So I'm taking complexes of OX modules, and I'm just insisting that the cohomology sits in degree minus 1, 0 and is coherent to the homotopy category of abelian cone stacks over X, which corresponds extending, so compatible with pullback and extending the H we just defined. So if you want H1. So the idea is, remember here, homotopic morphisms are considered the same. And so on this side, I have to pass to the homotopy category, means I start with a 2 category, where of course I didn't tell you how I make a 2 category, but I make a 2 category saying the morphisms are morphism of algebraic stacks, which are A1 equivariant, and the same for 2 morphisms. So this is a 2 category. So it cannot be equivalent to a category. So what I do is I pass to the homotopy category that says, okay, homotopic maps are the same. And so in particular, corollary to any, so corollary to Illusis construction of the cotangent complex to any morphism of schemes we can associate n x y. Let me put again an underline. So this is the abelian normal abelian cone stack, and you know, you could call it the normal cone stack, such that it's invariant under base change. It's flat local in y and étal local in x. So this means if I base change by a flat morphism of y, you get the pullback on x. And if you keep y and you change x by an étal morphism, you also get the pullback. And these two properties are exactly the same properties that I had for the cotangent complex, where n, and here of course there is an op. I forgot it here, but it's clear. Since I'm doing essentially like when I had coherent sheaves and abelian cones, I have to reverse arrows, where nxy is the image of what we had called the L twiddle of F, where this is the cotangent complex. So here the point is that you are trying to define an object which you know that it exists locally, because locally every map factors has closed embedding followed by smooth map. And you know, we have proven by all these exact sequences that the quotient stacks will be the same because we had Cartesian diagrams in the derived category. So we have it, but Fulton did, so we don't have to. The point is you have to glue this stuff, which is very complicated, because already gluing bundles requires some effort, and gluing stacks requires more effort because you have one extra cocycle. And here you have a theorem that tells you you don't have to do all this stuff, you know, these things just glue. So, and I mean, if you had asked me, do you believe that such a thing can just be true on the nose, I'm not sure I would have said yes. But of course, once you have seen the theorem of Deligne, it is actually not such a big stretch of the imagination. So Deligne has the same theorem in inverted commas for abelian groups, and we have it for vector spaces. Of course, it's more complicated because there is this spec sim and so on, so there is a, you know, inverting the arrows, but basically the idea that you can do it is really the same idea that is in the book of Deligne. The point is, Deligne, since he has the abelian group structure, has to keep track of the addition. And as we have seen, once you have an abelian cone, the correct thing to do is take care of the multiplication by scalars. Because once you have that, then it automatically make sure that the addition also is preserved. So this means now we have a very good understanding of how do we embed. In particular, we can say that by definition, let me summarize here that such a thing in particular, you have that F to E is a closed embedding if and only if H0 is an isomorphism, and H minus 1 is surjective. As we define an abelian cone stack is a vector bundle stack if you want, you can even say the rank of rank R in Z, because remember, these are things which can have negative dimension. If, let me call it E over X, if E over X is flat of relative dimension R. Remember that this is exactly how we found out which ones were the vector bundles inside abelian cones. And this is, on the other hand, a very easy lemma, that E is a vector bundle stack of rank R, even only if locally E is H of E minus 1 to E0 with both locally E minus 1 and E0 locally free of ranks R minus 1 and R0, and R is R minus 1 minus R0.
My intuition is somewhat, so if we say a map, you got the X is flat, we have tested on a string.
Well, the point is an algebraic stack comes with a smooth chart, and flatness can be tested, doesn't change. First of all, flatness doesn't change when you compose with another flat surjective map.
That's why you can have negative.
That's why, so is this actually this defining which properties you want?
You test it on the atlas.
You test it on the atlas, yes. That's, you know, actually I think, in fact, here I could be even better. I can say even only if this is smooth of relative dimension. It makes no difference, because again, it's the same as for vector bundles, and I tested on the atlas, and the atlas is E1. So E0, by definition, I had taken it to be locally free, so it's this kind of trivial actually. So locally it's trivial, but by definition, locally this is the description. No, because the rank can jump. I mean, a gerbe is something where the automorphism group tend to be the same. It has unique section. It is a gerbe if the morphism is surjective. I think that gerbe is something which has a locally a section, and the section is locally unique up to isomorphism. And I think you get a gerbe if this map here is surjective. Then you get a gerbe, in case you know what a gerbe is. So this is completely elementary. And the corollary, using the big theorem, now, you know, it's, then it tells you that A is, so that in the correspondence before, in the previous theorem, vector bundle stacks correspond to perfect complexes of perfect amplitude contained in minus 1, 0. So this is how you do this thing, that basically you have a local picture, which, okay, it's stacky, but it's stacky the most elementary way, because it's the easiest stack that there are, stacks which are quotient by a group. stacks that are quotient by an abelian group, so I don't even have to remember whether the action is on the left or on the right. So it's as easy as you can get. And then all you need is this big theorem of gluing, and you have Illuzy's construction of the cotangent complex. So the point is, this is already in the literature for I mean, as long as I've been around in the world. And this it wasn't, but there was a very similar result for abelian groups. So if you were aware of that, it wasn't a big stretch of the imagination that something similar could be figured out. And so now, of course, once you have all this picture, what can you do is you can do exactly the intersection theory. So, and then actually what we can do now, and we couldn't do back then in 95, is that there is a theorem, and here I want to put several names. So Vistoli 90 for the leading Mumford stacks over Q, and then there is editing Graham following an idea of Totaro for quotient stacks. And then finally there is Crash. And again, here there are some assumptions which I have no time to write, that there exists. So one can define Chow groups A D of X for X an algebraic stack, and D in Z, in such a way that extending the ones for schemes. So in particular for schemes you don't get the negative ones, and satisfying proper push forward, flat pullback. Of course this requires some care, because while defining flatness by what we were saying before is very easy, because you can check on, you can base change the second stack and bring it to be a scheme by a smooth map, and then you can take a chart for the rest. What the properness means requires a little bit of care. So it's not complicated, but it's a slightly subtle definition, the properness.
Just the usual value written with an extra extension field of the
Yes, exactly. Like what you have when you do stable reduction on curves. And finally, and of course with the property that, you know, the pullback on vector bundles does what you want, behaves well on vector bundles. I mean, I know this is very bad, but it just means that for vector bundles you have the same theorem. And finally, of course, you want that if X is irreducible of dimension D in Z, then you get a class so it extends actual cycles. Sorry? So if let me call this D0, it's not the same D as before. Behaves well on vector bundles. It has the same properties as for schemes, so that the pullback is an isomorphism shifted in degree. And this actually, all cycles come from the base. And it is an isomorphism. And so In particular, we can intersect with a zero section. We can invert. Yes. And you see, just for an idea, if you think, oh my God, what is this and how can people do that? The answer is actually, this is something that we have been long familiar with, only we didn't call it this way. So let me give you an example. And if we work over the complex number, this is not relevant, but it's just that I feel happier when I have the complex numbers holding my hand. And I call X, I just take BGM. So spec C modulo the multiplicative group. So this is non-singular, irreducible, because it's the image of a point which is irreducible, and of dimension -1, because this has dimension 0 and this is dimension 1. And well, so certainly it has something in degree -1, but in fact, you see, if you take C to the n and you quotient by GM, by the obvious action, you don't do anything fancy, you just multiply by scalars. If you want C0. This is a vector bundle of rank n, because it was a vector bundle before. It is a vector bundle after smooth base change, but being a vector bundle in smooth et al. And Zariski topology doesn't change. Sorry, it's a line. Yeah, it's a vector bundle. Sorry?
It's even a trivial one, because Cn to C0 is trivial.
No, it isn't trivial. It isn't trivial because we have done a base change. So, of course, every vector bundle, when you base change sufficiently, becomes trivial.
So trivializing
That,
C0.
yes, C0 is already trivializing.
C0 is
It's just a point. Sorry, it's just that I wanted to keep the writing short and symmetric. On the other hand, here there is an open substack, which is Cn minus 0 stack quotient GM, and this is of course Pn minus 1. So what I have is I have that AD of BGM, this goes into AD plus n of this Cn or BGM, and this is an isomorphism, and then this, as before, it has really all the same properties as you had for schemes. So if you go to an open subset, it gets surjective. So this goes into AD plus n of Pn minus 1. So this tells you that at least here you have to have elements. So this means that AD is non-zero for D in, well, you have to start in minus n and until minus 1. In minus 1 we know there is the class of BGM.
It's Cn modulo GM, no? Why BGM?
Oh, sorry, GM. Thank you so much. So this is what I get. And this was true for every n. So in fact, AD, I mean, it doesn't matter which n. So AD is non-zero for D. And in fact, what you can do is you can define A. You see, what you have is you have that Z of, so if you look at the case n equal 1, this object here this is a line bundle, and in fact it's a universal line bundle for any other line bundle, for giving a line bundle on something means giving a map to BGM, and this is exactly the line bundle it pulls back to. So what you get is that in some sense you have,
In fact, proving very clearly that it cannot be true.
in particular. And so in particular, if you take, call this line bundle, I don't know how to call it, let me call it L. Then you have that C1Z of C1 of L acts on A star of VGM. This is a graded ring, a free graded ring in one variable. And in fact, it is so this is it turns out that this is actually a free rank 1 module generated by the fundamental class. In other words, since this is smooth, you can define the notion of Chow ring of it. And this is exactly the Chow ring. And this is something people knew. I mean, this is something I learned by reading Grothendieck, that all Chern classes are all the cohomological information a vector bundle carries. The fact so that if you have some cohomology class associated to vector bundles such that it pulls back, then it is some combination of the Chern classes. Exactly. So it is precisely. So the analytic, topologically, this is the cohomology ring of algebraically, this is the classifying space. And what you can do, actually, you can prove, in fact, this argument that shows is non-zero can actually be used to show that this is an isomorphism. Because you see, here, the difference, so here I told you that this is an open subset, but the complement is in high codimension, which means in low codimension they have to be the same. And so you take the limit. Basically what you're doing is you're identifying BGM with P infinity. And the same result for the Grassmannian, for GLN, is done working with increasing Grassmannians. So it's really what you should view. You shouldn't view this as somebody is trying to do something completely abstract, but rather somebody is giving a geometric meaning to something we already knew. It's just a new interpretation of something we knew. So now that you have that, then what you can do is you can completely copy the construction. You remember we had this lemma of so there is one more detail which I haven't told you, that now remember, so we have all this big construction, we have translated the cotangent.
So this construction can be done for any primitivization of vector bundle on any stack, right? That's the question.
Say it again. So this construction is basically the way, let me just give you an idea. What Vistoli does is a kind of copy on the nodes the definition of Fulton, and then it turns out that he only gets something well defined if he passes to the rationals. Because I'll tell you in a moment why. The point is, in this case, the groups which are playing a role are finite. So anything which will go otherwise wrong is torsion, so when he goes to the rationals, he is fine. What do editing and graph do? They try to take the definition on the nose, and they find out it satisfies everything but this thing with the vector bundles. And so they decide with the, benediction of Totaro that this is not a bug but is a feature, so that somehow when you have a quotient stack, you have to consider all possible bundles, and you can make bundles in this stupid way. So you just take a vector space with a group action, where the fixed locus is in very high codimension. And you take the quotient, and what you get is a scheme away from something in very high codimension. And so this tells you that you can, for any given codimension you care to study, you can explore what's going on until that codimension. And finally, what Crash does is investigate how much you can push this for stacks which are only locally quotients but not globally. So it's basically the same idea, but you have a fine-tuned analysis to make sure that in particular it doesn't depend on the quotient, but also typically of stuff which is has an exhaustion, so that you have open substacks which are fine and then they grow until they fill everything. So now well, now you see if you have f from x to y any morphism, we have set of schemes, and in fact here I'm taking a morphism of schemes, so any morphism of schemes we can associate to it an xy which is h of LF twiddle, the normal cone or normal cone stack. I mean, it's the only normal cone this morphism has, and which extends the usual normal cone in case this is a closed embedding. In fact, you don't really need that this is a morphism of schemes. All that you know is that you can define this cotangent complex which is in degree -1 to 0, or any morphism of DM type of algebraic stacks. DM type means that when you base change with a scheme, you get a Riemann-Mumford stack, or it means that H1, that LF is in D at most 0. In general, it goes until 1. And what you want is in degree at most 0, and then you cut it at -1, and you get such a thing.
I don't understand this. In the base change, you want it like a DM, you want a DM stack.
Yes. You have an arbitrary morphism of Artin stack, and you say that the morphism is of DM type is whenever you base change with a scheme. So representable is base change with a scheme, get an algebraic space. Strongly representable, base change with a scheme, get a scheme. And DM type means base change with a scheme, get a Riemann-Mumford stack. And this is just equivalent to this, because an Artin stack is the Riemann-Mumford even only if the complex doesn't have a piece in degree +1. And so now, of course, we know that locally, Zariski locally, say on X, I have a factorization with, as usual, this is smooth, this is a closed embedding, and this is just the quotient of, basically by definition, modulo I pull back of T pi. Or if you want, because we know that this is how the cotangent complex looks like. And here there is a very easy lemma. So one, given such a factorization, CXM is invariant under the I pull back T pi action. So you have a group acting on a scheme and you have a closed subscheme. Being invariant just means that the action map factors via. And hence we get Cxy. This is again C underlined, a closed substack. So this is a closed embedding into NXY. And this Cxy is just the same thing with a cone. So this is a subcone stack in the sense that it's still a one invariant. It's a closed substack. Closed means that when you base change with a scheme, you get a closed subscheme. And two, these local constructions glue to a globally defined Cxy in NXY. And of course, 3, if y is reduced, irreducible of dimension d, which may be integer, then Cxy is pure dimensional of dimension d. So this is a very elementary computation. This is just something that you have everything is explicitly defined and you do some computation, and this could be an exercise in Hartshorne chapter 2 when you define you have the short excess sequence associated to the cotangent complex. This is not difficult. The gluing is the easier part, because when you are gluing closed subscheme, all you have to check is they are the same, because they can't be isomorphic. If you have two closed subschemes of something, either they are the same or they aren't. That there's no such thing as, it's the reason why the Hilbert scheme is not a stack but it's a scheme, is that you can't wiggle, there's no wiggle room here. So to prove this, what you have to do is you have to compare two embeddings with each other, and then you don't have to do it, you just take the book of Fulton, he has done it for you. So this part here essentially is an obvious consequence of what is written in the book of Fulton. And finally, this part is absolutely the same, because if y is reduced irreducible of dimension d, well, first of all, this cone, the property of being pure dimension of dimension d is local. So local on x, y and x is a risky local. So you can assume you have such a factorization, and then m is reduced irreducible of dimension d plus whatever relative dimension, and you do the computation and you get the same.
Just another basic question. What would be the analog of a splitting principle for a vector bundle of a stack? Is there something?
I think let me think about it when I have more time.
Another thing is, if you do have a vector bundle of positive rank on a stack.
Say it again?
Suppose you have a vector bundle of positive rank on a stack.
Yes.
And you take the projectivization of that bundle, if that
Yes,
makes sense.
it does, because it's something that commutes with the pullback, so it descends.
Are the Chow groups here and there related the same way?
I think they should be, because it is, I think you can get the whole thing of Fulton and check that it works for stacks, because basically...
And then classes could be also work out the same way as coefficients or something.
Say it again?
Again, classes.
Yes, yes, you have Chern classes, you have everything. Basically, the point is, like here, eventually the Chow group is really reduced to a Chow group for schemes. And so if you put it all together now, So let me, yes? So, well, you have to decide what is, okay, let me answer this in one, can I answer this question in, for regular embedding, CXM and NXM are equal, and hence, if the morphism is LCI, then, so maybe I should say that, and if F is LCI, this implies that I is, if and only if I is regular embedding, and this is equivalent to this implies, well, this is equivalent to CXM is equal to NXM is a vector bundle. And so in particular, this tells you that the normal cone is the normal sheaf is a vector bundle stack. Because this property, the property of being of a closed subscheme being everything is local, and the property of being a vector bundle stack is also local on the basis. So these two things can be checked on a splitting. And of course, sorry, if F is locally LCI, so if F has the cotangent complex, which is perfect in -1, 0, then you just get a global object without assuming that you have a global splitting. So let me remind you of Fulton, the one I told you. Fulton was that let F from X to I 17 is by, yes, for morphism of scheme, closed embedding of schemes with NXY with a choice of a closed embedding, and this is a rank R vector bundle, then we get, if you remember, an FE Apachrik, we can define a pullback in a R of X to Y, which meant for any base change we have a pullback map which lowers degree by R. And the special case was, e.g., if F is a regular embedding of codimension R and E is just an XY. And so what we get is we get an analogous proposition given F from X to Y, a morphism of algebraic stacks satisfying the assumptions of crash, so that you can have that have a with crashes assumption on to get Chow groups. E.g., they can be schemes of finite types over K. We remember here we always have a fixed field. Given such a morphism of the linear Mumford type and an embedding of the normal, a closed embedding of abelian cone stacks into closed embedding of abelian cone stacks with E, a vector bundle stack of rank let me of rank R, then e.g. F LCI morphism of schemes of relative dimension R, and in that case N is E, sorry, and this is not LCI but local LCI, then we can define the same thing, absolutely. Replacing in Fulton's construction the normal cone cones by normal cone stacks.
Just a point of clarification, very silly question. We have a global LCI map.
Yes.
Then do we need stacks to make this?
No, of what?
Of schemes.
No, we did last week.
Yeah.
Yes. But if you have an LCI map which doesn't have a global factorization, I don't know how to do it without algebraic stacks.
The algebraic thing is a stack, right? When you're going modulo phi of the star p phi of.
No. So this, yes, this is anyway exists whichever ways. This is just an object which I can decide to look at or not. The point I think you wanted to make is that you don't need to go this roundabout way if you have a global factorization. What the reason where it's not so many cases I know where you don't know that you have a global factorization. What on the other hand definitely is true is that there are a million of cases in which you have such an embedding, but you don't have a factorization to which you can apply this. Or, well, again, a posteriori you can find one, but then you have more than one, and then you have to check that everything glues. But really the natural object is this thing here. So it's something related to this morphism. And by the way, okay, so, and remark, in fact, this is something which I think is a bit difficult to find in the literature, but there is more has been generalized, so the generalization, the degeneration to the normal cone extends to this case. Of course, it's not so simple to construct anymore. So you have to throw a lot of descent to the problem.
Blowing up stacks as a sense is not going to accomplish.
Well, the problem is blowing up stacks is fine because blowing up behaves very well under smooth or flat base change. But what you can't do is blow up something which isn't a closed embedding. So, I mean, at least maybe you can, but let me qualify. I can't blow up something which is not a closed embedding. So, what you have to do is you have to essentially to add some factorization and then prove that what you are doing and descend down so that show that what you have done descends. And it is a serious exercise in descent theory, and I mean, and in fact this thing and in a suitable sense, and this I think I learned it in a paper of, I think it's Crash, Kim and O, but don't quote me on that. I should have checked it this morning, but instead I was busy pestering Ramadas to get me a glass of milk, so I didn't. Okay, so anyway, we can check where this, the point is there is not a theorem, that, paper which says, hey, people, I announce you this fact that the relation to the normal cone extends. I think because these people thought that it wasn't so difficult. And then what you can prove is that this is functorial. And this has been proven by a former student of mine who's very smart, currently at London. She's called Manolake. And functoriality looks, well, you know, everything is functorial, why not? But in fact, what functoriality requires is to do this twice. So you have two morphisms, and what you do is you first degenerate to the normal cone of the whole morphism, and then you degenerate further to the normal cone to the normal cone. So it is not a trivial thing. And so okay, so now we have this proposition where we have the feeling that, okay, big deal, we have been, you know, we have taken exactly the same assumptions and we just changed the obvious. So how do we ever check these assumptions? And so first of all, we had our dictionary between algebraic. Oh, and the other thing I didn't say is that this doesn't change if you replace a morphism by an isomorphic one. So here the result depends only on the homotopy class of this map. So on this morphism up to two morphism, you still get the same map in the Chow. And then what you get is recall. So by definition, let f from x to y be a DM type morphism of Rth x. A morphism phi from E dot to LF twiddle in D is called an obstruction theory if
two notations you use. One is D minus 1, 0 of covariant sheaves on x, another is x with covariant at the bottom. What is the difference between these?
So let me recall D whatever co x. This is the derived category based where the objects are complexes of coherent sheaves, and D x co is the right category where the objects are complexes of sheaves of OX modules with coherent cohomology. So there is obviously a morphism here, because if you have a complex of coherent sheaves, then cohomology is coherent, and if X has enough locally frees and you are putting a suitable decoration here, typically you want bounded above or bounded or -1, 0 or whatever. So the point is you don't want to go to infinity, then this will be an equivalence, and otherwise not. So typically the point is that the cotangent complex for Artin stacks is here, and in general it doesn't have a very good reason to be here. And by the way, the correct reference for the cotangent complex of a morphism of Artin stacks, the recommended reference at least is a paper by Olson with the title something like the, so this is at least one which is easy to find, because the result is either in the title or in the abstract. So it's if the induced homomorphism n xy in E is a closed embedding. So the point is, if we can find an obstruction theory which is perfect in -1, 0, then we get a pullback. And then the big result, and this is related to what we had discussed the other day, is that proposition, and this is a very easy local result. It's a simple consequence of what we did the other day when we were doing deformation theory. Given a morphism as above, it is an obstruction theory. And let me be, since we have -3 minutes, let me be very informal. If E dot is as good as L for computing tangent and obstruction at geometric points of X. So the idea here is what? You remember that we had seen that the cotangent complex gave us information to the following problem. I have a semi-small extension of fat points. I have the larger fat points mapped to here, the smaller fat points mapped to here, and I want to lift it. And I had an obstruction vector space, and once the obstruction vanished, I had a tangent vector space that told me in how many ways I can do it. And what happens, these two vector spaces can be computed in terms of this. You pull back this at a point, and you dualize, and you take kernel and co-kernel. Now, if you use this map, you will get a map from the tangent to something here, and a map from the obstruction to something here. And what you want, remember, the tangent was completely determined, because the tangent was the set of lifting is a principal homogeneous space under this vector space. So this determines the vector space. The obstruction wasn't quite determined, because since we had only to check whether it was 0 or not, we can always embed it into something larger. And it turns out that since we are embedding into something larger after we have dualized, this precisely corresponds to the surjectivity on the h-1 level. So the point is, once the formation theory tells you to expect, this is what we were saying at the colloquium, once the formation theory tells you to expect a dimension, so how do you see that you have a perfect complex? Well, the first evidence is that the rank at every geometric point is the same. And the rank is the rank of the, it's the usual, the basic theorem of linear algebra. It's the difference between dimension of the kernel and dimension of the co-kernel. So if you have one expected dimension at every point, then it's usually solid evidence of the existence of some obstruction theory. And what you need is, of course, first of all, you need enough derived category to take these pointwise vector spaces and make them into a complex. And then you need to look at the properties of the, Illusi wrote about, two thick volumes, so there's plenty of morphisms, and you play around with them. There's a number of natural maps, and usually you will have a map which does what you want. So the point I think I want to make is that this lemma state at the end of a chapter, at the end of the book, because there aren't that many examples. But these could stay at the beginning of something, not at the end. Because once you have this together with this remark, then you immediately get immediately. In fact, this thing was provoked, this development, by the desire to actually figure out what Gromov-Witten invariants were. But then once it was there, it was used for Donaldson-Thomas, it was used for Pandaripande-Thomas, and it is used again and again and again, because now this is a standard technology that you can use. Okay, thank you very much. It was great lecturing here.
I guess
Yeah.
from the audience, it's been a pleasure having you here. One question.
Here's a
Question.
What?
You define abelian cone stacks, right? So, I mean, why don't you, like, is there a way to define cone stacks without going into NX or then defining a closed invariant?
I would say a cone stack no, I would say a cone stack is a stack with an A1 action which locally is a closed substack of an abelian cone stack, and equivariantly for the A1 action. And then what happens is, just like in the cone case, there is a canonical one. So there is one which is smaller than all the others, which is the abelianization. So the point is, it's a local property, and then it becomes global.
So I hope this is the first time I'm doing the future courses that you come with more on stats, but more on other things. So we hope that she's going to come back again in 2015. Maybe I'll make a public announcement.